Today I want to consider some consequences of the mean value theorem. So the first is what is called the maximum principle. For harmonic function. It is the following theorem. Let me formulate this theorem. Consider domain D with a boundary gamma and the n-dimensional space. And suppose u of x is twice differentiable inside D, and it is at the same time continuous in D bar. So let me explain. D is interior of this domain. D consists of all points such that they have some ball of non-zero radius with center as x, and which is inside domain D. So D is an open set. And gamma is the boundary, so D bar equals D union with this gamma. So D with the boundary. So the function u is twice differentiable inside D and continuous up to the boundary. Yes, the first thing. And Laplacian u equals 0 in D. Then we have the first statement is that maximum u of x over all x in D bar is equal to maximum u of x over x in gamma. So the maximum of the function u is achieved on the boundary. Now, first of all, why the maximum is achieved? We know about the function which do not achieve a maximum. No, for example, if the function goes to infinity when we approach the boundary. But if the function is continuous inside and including the boundary, yes, in D bar, then by the classical theorem, there is a point where the function achieves the maximum. Yes, it is studied in analysis. And second, if maximum u of x is achieved inside D, then u of x is constant in D bar. So not only, so the first part is called the maximum principle, says that the maximum is achieved only on the boundary, but maybe the same maximum can be achieved inside. And second is a stronger statement, which is called a strong maximum principle, which says that if maximum is achieved in some internal point of our domain, such that it is a positive distance from the boundary, then simply the function u is constant here. U was harmonic function. So harmonic function achieves its maximum on the boundary, and if it achieves a maximum at internal point, then this function is constant. Now let's go to proof. And interesting thing that the second part is better to prove first, and then the first part follows immediately. So we prove the second part, the strong maximum principle. So proof of the second part. So consider some internal point x in D. If it is internal point, then there exists a sphere S of x with some radius r. There exists a sphere which is entirely contained inside D. So S of x r inside D. And we have the mean value theorem by the mean value theorem. U of x equals 1 over area of S of x r integral over S of x r u of y dsy. Yeah. So it is integral, and we divide by the area, and we have the mean value over this sphere, and ux is equal to this mean value. This is what was proved last time. It was a little bit harder theorem because it required some calculations. And now one small thing. So this is x, this is S of xr. We assume that maximum is achieved at the point x. So we assume that u of x is maximum u of y in D bar. Yes? What does it mean? This means that u of x is more or equal than u of y, or all y in D bar. All y in this domain. In particular, ux more equal u of y for all y in S of x r. So everywhere on this sphere, u of it is x, this is y, u of y is less or equal than u of x. And now I want to prove that u of y equals u of x. So so it is claim u of y equals u of x for all y in sphere, for all y. No, to the contrary, as you suppose u of y0, there exists y0 in the sphere such that u of y0 is less than u of x. Yeah? Then u of y less than u of x for y minus y0 less than some epsilon. Yes, because u of y is continuous on S xr. Yeah? The function u is continuous, so if at the point y0 it is less than, strictly less than u of x, then there is some small neighborhood where it is still less than u of x, because the function is continuous. If u of y less or equal u of x for all y in S of xr, then the mean value of u of y integral over S of xr, I'm sorry, uh, 1 over S of xr integral over S xr u of y dsy is strictly less than u of x. Yes? No, because the function everywhere is less or equal u of y less or equal u of x everywhere here, and there is some piece, say spot on this sphere where this function is strictly less. Then integral is strictly less than integral u of x. Yes? So it's less than u of x. This contradicts the effect that 1 over s xy area integral s xy u of y dsy equal u of x. Yeah? And so we assumed that there is some u0 such that u of y0, u of y0 strictly less than u of x, and have an immediate contradiction to the fact that the integral should be equal. Yes? This means so we have two things. That u of y is more or equal u of x. If it cannot be less than u of x, so it is more or equal. But u of y is less or equal u of x, because x is the point of maximum of u of x in D bar. Hence, so uy more or equal, uy less or equal for any y on the sphere. Hence, uy equals ux. So we prove that for any point, it is x, it is y, uy is ux on the sphere S of x with radius r. But all this sphere, all this ball is inside our domain D. So this means that if you take any other sphere with centrum x and radius less than r, then we can say the same. On this smaller sphere, also we have that y equals ux. If x is here and y is on smaller sphere. So hence u of y equals u of x for all y inside the ball with center x and radius r. Yeah. So it was true for the larger ball, so it is true for any smaller ball. Yeah, clear? So we proved that our function u is constant, is equal to u of x in some ball. So what is this ball? How to find this ball? Where the function u is constant. So this is our domain D, this is the point x. So we have to draw a ball, take maximal ball such that is inside domain D and the boundary. Now let's take a little smaller ball. Yes? So the ball whose radius is, say, r equals 1/2, say, distance from x to gamma. This is gamma. Yeah. So we take any point x. This is the closest point on the gamma. Let us take 1/2 of this distance. It is enough. And everywhere in this ball, say b of x, r equals r capital. In b of x r u of x is constant. Yeah? So we found at least a piece of our domain where the function u is constant. If you assume that at some point this function achieves its maximum inside domain D. Now let us take any 2 points. Okay, it is the point of maximum, say here x, and this is any other point, say z. How to prove that claim u of z equals u of x? Let us draw a curve inside our domain D, curve gamma. Gamma is a curve connecting, continuous curve connecting x and z. For example, it can be a piecewise straight or like the curve like this. Now, if at every point of this curve we find the distance from this point, say t, to the boundary gamma, then we have the function, say f of t equal distance from t to gamma along the shortest segment. And take r equals 1/2 minimum over t in gamma f of t. Yes? So it is r is such a number, such a small number, that if you take any point t here, then the ball of radius r does not reach the boundary gamma. Yes? And then let us do the following. The function x is maximum, point of maximum. So this means, as we proved, that the function u is constant in the ball with center x and radius r. R is the same for all the points here. Now let us take the last point on the curve, say, let's call this point t1. The point t1, on one hand, the value of the function u is equal to the value at the point x, so at the point, so u of t1 equals u of x, equals maximum u of s for s in d bar. Yeah? So it is also the point of maximum. So now we can draw another ball of radius r with center in t1 and take the point t2, which is the last point in at the t1 where it intersects with our curve gamma. Then you draw the ball with center at t2, here is t3, and so on and so on. After a finite number of steps, we reach the point z. Yes? Why finite number? No, it is still other theorem in analysis, theorem about the finite covering, which if you know, it's okay. If don't know, no, I am not teaching analysis. So let us believe now that it is true. So this means that we found the proof that u of t2 equals u of t1 equals u of x equals, and so on, equals u of Tn, and the ball with center Tn contains the point z equals u of z. Yes? So, and this is true for any point z, so it is true in the whole D. So we proved that u of x is constant in D, yes, but u of x in C of D bar, which is C of D union with gamma. Yeah. So if you take any point on the boundary, y here, then we consider a curve, a continuous curve, which goes inside our domain D and tends to the point y, and then u of y is limit u of x when x in the curve, say lambda, x goes to y along lambda. But u of x equals limit constant, let us denote it by u capital, of ux, limit of u is constant, which is equal u. So this means that not only inside our domain D, but also on the boundary, this function is constant. Now, so this means that we have proved our theory. To mark this, I write this symbol. Okay, okay means we have proved the theory. And now I wanted to show one fundamental implication of this theory, this principle, maximum principle. Yes, and one moment. The first part, principle, maximum principle. So it's stated that if the maximum is achieved somewhere in our domain D, including the boundary in D bar, then the maximum is achieved on the boundary. No, instead, in fact, if it is achieved on the boundary already, then nothing to prove. If the maximum is achieved inside domain D, then we prove that the function is constant. If it is constant, then the same maximum, the same value is on the boundary. Let us not hurry. So, by the same way, same reasoning, minimum u of x when x in D bar equals minimum u of x, x in gamma. It is the first part. The second part, if minimum u of x, x in D bar is achieved at x in D inside, then u of x is constant. Yeah, and if you take these two statements together, we have the third. The next statement. First, maximum model u of x when x in D bar equals maximum model u of x when x in gamma. So, no, maximum is either positive or negative or zero. Yes, so if it is positive, I mean maximum, yes, the function of the model u of x. So if you take the point where this is maximal, this maximum is either positive or negative. If it is positive, you use the first statement. One moment, let me repeat it. Maximum model u of maximum u of x in D bar equals maximum u of x in gamma. And second, if maximum u of x in D bar is achieved at x inside D, then u of x is constant. Yes, now the same about minimum. And the last is about maximum of modulus. If maximum module u of x in D bar is achieved at x in D inside, in inner point, then u of x is constant. Yeah. So we have these three statements. Now the third statement is the most useful. No, it depends on what problem you are solving. And now I wanted to formulate and prove the following. It is called uniqueness theorem for the Dirichlet problem. Uniqueness theory. So consider again domain D with boundary gamma, and consider the Dirichlet problem. Find u of x, which is C2 in D, intersection C in D bar. Yeah, so the function is twice differentiable inside and continues up to the boundary, such that Laplacian u equals f in D, u on the boundary equals g. So it is our old friend Dirichlet problem. So the statement is solution u of x to this problem is unique. Unique means that if we have two solutions, say we have obtained one solution by one method, other solution by other, principally another method, then this solution coincides at all points. Yeah, so there is no, it is impossible to have two different solutions of this equation. Here the problem, the question a little bit philosophical, why should they prove such theorem? Is it not obvious then solution of to the problem is unique? No. Let me bring you a simple example, but it has closer relation to this problem than it was then you can think. So consider a system of two linear equations, x plus 2y equals 3, 2x plus 4y equals 6, for example. This problem has not unique solution. Yes? Because in fact these two equations are equivalent. I took the first equation, multiplied by 2, have the second equation. So this means that if you consider all solution of the first equation, it is 3 2y, it is 1 and 5, and draw a straight line through these 2 points. Every point on this line is solution, its coordinates give solution to the first equation and to the second equation. So here we have infinitely many solutions. Yes, solution is not unique. So, what is the difference between this problem and this problem? Is there some difference? The answer is that such a difference, of course, exists because it's just simple algebraic problem, and this is a much more complicated problem of differential equations. But in fact, the principal difference is not here. And maybe in a couple of minutes I will present you very close example, close to this equation and close this, where the difference, the solution of such equation is not unique. So for now, let me produce the proof of this equation. Proof of this theory. The proof. Suppose solution is not unique. And V of x is another solution. Yes, assume that there is another solution. Define W of x equals ux minus vx. So what equation it satisfies? Laplacian W equals Laplacian of u minus Laplacian of v. Laplacian, it should satisfy the same equation. So Laplacian u is f. Laplacian v should be also f minus f equals 0. Identity equals 0 in the whole domain. W on the boundary gamma equals u on gamma minus v on gamma. U on gamma is g minus g equals 0. So we have a function u such u in C2 of d and C of d bar. Yes, don't forget this. Laplacian u is 0. U on gamma is 0. So maximum module u w, it is not u, w. Sorry, w delta w and w on gamma is 0. Maximum module w of x in d bar equals maximum module w of x in gamma is 0. So no, module w is non-negative. If it is maximum is 0, then w is 0. W of x, identity 0 in d bar. So u of x minus v of x is 0 in d bar. U of x, identity equal v of x in d bar. So we, using the maximum principle, we easily proved that the function solution is unique. If there is other solution, then the difference is 0. And what about this example of the problem such that its solution is non-unique? So when we studied the string equation, we had also the Neumann boundary condition. Neumann boundary condition is derivative on the boundary should be given for the string. If this derivative is 0, then it is corresponds to the free endpoints of the string. Yes? It can move up and down the string, but the vertical force is 0. So here I write the analog of this boundary condition for the Laplace equation. So Laplacian u equals, say, f in D, U du dn y on gamma is G on gamma. Yeah. So instead of the value of the function, I give the normal derivative of the function. Yes. So it is more or less obvious that solution is not unique. Solution is non-unique because if u of x is a solution, then u of x plus c is also solution. Yeah, if you add c, some constant to u, then Laplacian will not change. Yes, and the derivative, normal derivative, will not change because derivative of the constant is 0. So solution is non-unique, you see. But does there exist solution? In fact, next time I'm going to prove the existence of solution. But here I consider simple case when solution does not exist. I start from the Neumann equation. So consider the following example. It is some domain D, the boundary gamma, and I write Laplacian u equal 0 in D. Yes? This is the point y, this normal vector and y. D u d and y on gamma equals, say, 1. Why not? So consider this problem. So this is a particular case of the Neumann problem. The claim is that this problem has no solution. No proof. Let us use the Green's formula. So integral over d Laplacian u dx equals integral over d Laplacian u times 1 dx equals integral over d Laplacian u times 1 minus u times Laplacian of 1 dx. No, because 1 is constant, its Laplacian is 0. And by the Green's formula, it is equal integral over gamma u d of of 1 d and y minus 1 times du d and y, no, of y, u of y, ds gamma, dsy. Yes? No, remains here only this term. No, if it is in this order, we have to put here minus and here plus. So this is 0, and it is equal to integral over gamma du d and y of y dsy. Yeah, and now let's see. Laplacian u is 0. Yes? And so the left-hand side is 0, and the right-hand side is integral over gamma du dny 1 times dsy, which is module S, module gamma. Module gamma is the area of gamma. So here is 0, here is area of gamma, which is positive. So this means this contradiction. So what was our hypothesis? Our hypothesis was that U is a solution. There exists solution U. So this means that solution does not exist. Yes? And I would say that mechanism of this non-existence, I'm not going to go deeper in this issue, maybe a little later if we'll have half an hour. But this means that existence of solution is not self-evident. Sometimes solution exists, sometimes it does not exist. And we have to, every time we have to prove and find the reason why does solution exist. Because if solution exists somewhere, then nearby there is other problem where solution does not exist. So we have to be careful with existence of solution. Okay, so let us finish this piece, and I will return soon with the next piece. For now, have a good time. Bye.